and I will start the recording. So we are starting today with chapter 2. Before I get into chapter 2, do you have any questions about chapter 1 or chapter E? Okay. So we're starting with chapter 2. In chapter 2, we actually need extra time on that chapter because most of the concepts here are abstract. So this chapter covers the quantum mechanical model of the atom. So the idea is, as we are starting this chapter, I'll quickly review over what we covered before. We talked about the different models of the atom. And the most significant one we started off with was Dalton's atomic model. So you say Dalton's model. And his idea was the atom was round and it was indivisible. So we'll call it the indivisible atom. There was nothing inside of it. And then we had J.J. Thomson. And his idea was the atom was round, but it had electrons dispersed throughout. And these electrons were negatively charged. The core of the atom was positive. So the overall atom was neutral, and this is called the plum pudding model. Okay. So we had Dalton's model, we had J.J. Thomson's model, then we had Rutherford's model. And Rutherford, if you remember, set out to help slash friend JJ to prove his model. Come to find out, he discovered. So his model is called the nuclear model. And the nuclear discovering the nuclear positive charge is concentrated in the nucleus, and the mass of the whole atom is the nucleus. Of course, around the nucleus you have electrons, but they're very fine. They are massless. They occupy pretty much the whole space in the atom because the nucleus is very small, very dense, and in the center of the atom. So this is a nuclear model. Okay, so we talked about these three significant models. In this chapter, we'll be talking about two additional models, one being Bohr's model. So I'm going to draw it while we're here. Bohr's model, I would say, is the most popular model of all the models because Bohr's model, B-O-H-R, Bohr's model, essentially it's the one that you see in Big Bang Theory, Jimmy Neutron, most TV shows. When they're trying to illustrate chemistry or the atomic model, they talk about Bohr's model. You do have a nucleus, and this model is called the planetary model. So you have the nucleus in the center that's positively charged, and then you have electrons orbiting around the nucleus in specific orbits. So I'll put E for electrons. You have electrons in the atom orbiting around the nucleus. So I'm drawing these right here. Okay, and so this tends to be the most common or the most popular model of the atom, and scientists use this a lot. Chemists, not so much. We use it for a means to an end. When we talk about a lot of the behavior of the electrons, it's a lot easier to illustrate that behavior looking at the planetary model versus the quantum mechanical model. But in reality, chemists tend to focus on the quantum mechanical model because that's the newest model. So with this one here, it's difficult to find pictures of it. We have quantum mechanical model. I can say its name is not as fancy, it's not as relatable as the planetary model. The planetary model follows the idea of the planets, right? How the planets are related to the sun, their positions, their orbits, and everything. The quantum mechanical model, the average person who contributes this model. You have a Planck, you have Heisenberg, you have Schrodinger, etc. There's so many different scientists who work together to ultimately put together the quantum mechanical model. So the quantum mechanical model is based on the work of so many scientists. So we don't really give credit to just one scientist. Okay, so I'm going to attempt to draw this model. It's a very complex model. This model is based on not orbitals, but orbits around the nucleus. Sorry, not orbits, but orbitals around the nucleus. So here, these circles are orbits. In the quantum mechanical model, the circles are orbitals. Okay, what's the difference besides the AL? The orbits are 2D paths that the electrons have, fixed path electrons have around the nucleus. The orbital is a 3D space that the electrons travel in around the nucleus. And then with the picture up here, Bohr's model that's very close to the quantum mechanical model, the only path the electrons can take is circular or orbital, like it's round, okay? Here, in the orbitals, the path that the electrons can take has different shapes. So one of them is round, like this, and it's actually spherical, not circular. This is more like a sphere. And so we'll get into all that. Now I'm talking about the overview. The other possible shape, I'll use a different color to illustrate that, is a figure eight. It's like a dumbbell shape, like that, like that, like that. The other shape we see here, I'll use the blue color, is a clover leaf shape that looks like that. And it gets bigger as you move away from the nucleus. Okay? As you can see, this is already getting very complex. It looks like I'm just scribbling stuff. But the electron, depending on what elements it's in, depending on what energy level, has variations of spaces, 3D spaces it can occupy around the electron. So this chapter will focus on the following two models. Okay. So now we are working up to the model. As I said, there's a lot of scientists that contributed to this model. So we have to go into the area of quantum mechanics and chemistry, the atomic model that explains the strange behavior of electrons. So scientists notice that electrons have strange behavior. Now remember, when we're looking at the atom, as far as the identity is concerned, the identity of atom, we get this from the protons, right? The proton number. But the behavior of the atom, for that, we get from the electrons. Okay, so when they're talking about the behavior of the electrons, they're technically talking about the behavior of atoms. So we're told here, early 20th century scientists began investigating absolutely small quantum world. Okay, so when it comes to very small quantum world or very small particles, that is essentially the quantum world. They list a group of scientists here. You had Einstein, Bohr, de Broglie, Planck, Heisenberg, Dirac, and then Schrödinger. These are a few of the scientists. So together, these people are credited for the quantum mechanical model. Their work laid foundation of our current understanding of matter and its behavior at the subatomic quantum level. Okay, so remember, you have the atom, that's the atomic level atom, and then within the atom, you have subatomic particles, the particles that are found inside the atom. And these are protons in the nucleus, neutrons also in the nucleus, and then we have electrons outside the nucleus. So you have these subatomic particles, particles inside the atom. Okay. Scientists were focusing their attention on these subatomic particles. They were excited to have discovered them. They wanted to know their behavior. Remember, protons, identity of the atom. Neutrons, we'll talk about this in 1412 if you take that class. Electrons, I mean, these add to the mass ultimately, contribute to mass, but they have a more important purpose in 1412. But I'll mention it right now since I'm here. Neutrons help with stability of atom, okay? And then electrons with the behavior. of the atom. Okay, so moving on, scientists notice that electrons behave strangely. They were behaving in a way that the scientists did not predict. Electrons appear to exist in two conditions, either the wave form of the electron or the particle nature of the electron. They had a natural duality. So, regardless of the element they were studying, electrons had dual nature. Okay, so before I go into the details of what dual nature means, um, they tell you what the dual natures are. You have the wave nature and you have the particle nature. So it would be like saying, well, human beings have more than one form. We have the physical form, which is our body. You have your spirit and you have your soul, right? So if you were to describe the different existences of humans, you could argue, you could say people think about different things, that for a human, you have the physical, which is the body, you have the soul, and you have the spirit. I've heard people say, "Oh, this child has an old soul." I'm like, exactly what does that mean? I guess the desires they have, the way they see the world, is like somebody who's lived a very long life, right? It's just a description of the way the person is behaving. So you could argue humans have three natures. Okay? Electrons have dual nature. There is one nature where they exist as waves, another nature where they exist as particles. So when they're existing as wave, they will exhibit all the wave-like behaviors. That's what will show the scientists, oh, here is the electron. We were studying the electron. All of a sudden, we're getting wave information. When they exist as particles, they'll be like, wait a minute, we're studying electrons. All of a sudden, we're getting particle behaviors and characteristics. So we're told here the example. Electrons presented particle behavior when they possessed mass, volume. Now, there are many other particle-like behavior, but when the electrons are able to possess mass and volume, you can weigh the electron, you can figure out how much space it occupies. Those two are part of the many behaviors particles have. Now, for you to see this behavior, we're told here you have to have a certain set of experimental conditions. So the experiment almost has to be geared for the scientist to see this behavior, which is mass and volume. Okay? Under different set of conditions, which may be intentional or accidental, the same electron will all of a sudden have different behavior. The same electron will exhibit energy-like properties. In this case here, you can say it will have a wave, it can give off light. So trying to bring it down to, I guess, more regular level, not the deep existential level, the regular everyday level, it would be like you have a friend that changes their behavior completely when they meet other people. They act regular, they act relatable, and then when certain people walk by, they start acting, standoffish, aloof. That happened a lot when I was in school with certain girls. If they liked a guy, they act fun, they act regular. When the guy they liked walked by, their personality changes completely. So somehow that guy was that different set of experimental parameters that just changed their behavior. And then when that parameter was gone, aka the guy, all of a sudden they default back to their other personality, and you're like, what is all of this? Just be you. Anyway, the idea here is matter is able to exist in more than one form. So this wave particle behavior, the switch back and forth, duality of matter is actually made into a rule. The fact that electrons do have two natures, a wave nature and a particle nature. You see one or the other depending on experimental conditions. We're told here much of the behavior of the atom is determined by the electrons. I've already specified that. The model that we're trying to learn about, which is ultimately the quantum mechanical model, explains the manner in which electrons exist and they behave in atoms. So we know electrons are inside the atom. We know electrons are not in the nucleus. And we're told here, electrons have a light wave energy in nature, but not the particulate nature. Okay, so once again, depending on what the experiments are set to be or the conditions are, you may see either light wave behavior or just wave-like behavior or particulate behavior. So in talking about the model in general, there's certain characteristics they're highlighting. And you see that in the model, there's certain characteristics that are highlighted more than others. So we see more of the light wave behavior, not as much of the particulate behavior. But we're going to be discussing rules that talk about both behavior. So we're told here the electrons can no longer be viewed just as particles orbiting around the nucleus, but as clouds. So the particle orbiting around the nucleus, you're talking about Bohr's model, the particle, aka electron, orbiting around nucleus. When we talk about the quantum mechanical model, what they're saying is don't see the electron exactly like what Bohr was talking about, a particle orbiting around the nucleus. But now we want you guys to graduate and get to a higher level where you see the electron more like a cloud, like a mist that has many probable positions. So instead of seeing the electron as a particle that's right here and not here, 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 see the electron in all the position it occupies around the nucleus. So in other words, see the electron like a cloud, not a particle. So the particle will be like a pebble, something that has definite, you know, dimensions, right? You want to see the electron as something that's occupying a lot of space. So we'll get into all that when we get into the quantum mechanical model. Okay, so the quantum mechanical model, once we learn this, what are we hoping to accomplish? We are hoping to see periodic trends, behaviors that we see of the electrons within the atom that affect the atom behavior. So you have atomic behavior that is predictable, atom behavior, and periodic table. These are called periodic trends. So there's certain characteristics, mannerisms of the atom in the periodic table that is very trendy. When we say it's trendy, that means that along the period, the behavior becomes more prevalent or maybe less prevalent. Down the group, the behavior intensifies or becomes less intense. Okay? We'll see the behavior of elements in chemical bonding. We'll see the colors of the atoms and the atomic size. These can all be tied back to that quantum behavior, the behavior of the electron like a light wave or a particle, but more so the light wave behavior. Okay? We'll be able to answer questions like why some elements are metals, while others are non-metals, why some elements gain or lose electrons. Okay, some gain to form a anion. Some lose to form a cation. Why some are very reactive while others are very unreactive or inert. Why do we see these patterns along the periodic table? This will all be explained looking at the quantum mechanical model, the light wave behavior of the electron, mostly more than the particle behavior. Okay, so to understand the electron, to understand electron behavior as a wave, we will detour. Okay, we're trying to understand the behavior of the electron as a wave, but the only reason why we're able to recognize that behavior to be a wave was because at this point, scientists knew the nature of light. So even though it seems like we're detouring into an unrelatable chapter, we are trying to understand the behavior or review the behavior of light to see the characteristics of the electron when it behaves as a wave. Okay, so we're going to be looking at the wave nature of the electron as we study light. So we're told here to understand the wave nature of matter, we study the behavior of light. What is light? Light is an electromagnetic radiation that is usually released from a body. Okay, so we have a radiation composed both of the electrical part, and this radiation is influenced by the electrical field and also the magnetic field. So once the radiation is released, both the electrical field and the magnetic field influences radiation. And so we're told that here, both of them are influencing the radiation. The radiation has a specific speed in vacuum. So it doesn't say so here, but electromagnetic waves tend to move at this speed right here, speed of light, so to say, in vacuum. We're going to be looking at the electromagnetic spectrum. Just remember, all those waves, since they are electromagnetic in nature, they will all have the same speed, and their speed is 3.00 times 10 power 8. Some books say 2.99 times 10 power 8 meters per second. Either one is fine. So go ahead and write. I would say this is an easier one to remember. You need to write this down. Speed of light. The symbol for speed of light is c, okay, in a vacuum. And so for our calculations, you're going to be needing this number. So now as we look at the electromagnetic waves, we're looking at the behavior and characteristics of the energy in the waves. So the first thing we see here is something called amplitudes. Waves have amplitudes, and waves are judged by their amplitude. Exactly what is the amplitude? In this picture on the right, we're being shown a wave, okay? The amplitude is the distance of the wave from this axis drawn here, from the core, all the way to the top. The top part of the wave, the core, is called the node. The top part of the wave is called the crest. Ooh, crest. The deepest part of the wave is called the trough. So the node of the wave is the center, okay? So if you measure the center of the wave or the core of the wave all the way to the highest part, that is called the amplitude. If you measure the core or the center of the wave all the way to the lowest part, this is also called the amplitude. So what do we get from the amplitude? The intensity of the light. I recently remodeled my bathroom. When I say recently, I mean a couple of years. It's been a couple of years. And I remember when we're trying to buy the light bulbs, you're thinking this doesn't relate to life, right? We're trying to buy the light bulb, and we tried to buy a light bulb that wasn't necessarily, it wasn't super energy efficient, but we wanted something that was semi energy efficient. We had to go through light intensities. And I mean, there were so many options to pick from. Do you want it to look like daylight? Sure, since we're going to be walking into the sun after we're done putting on our makeup or whatever, getting dressed, sure, daylight. Do you want it to be very intense? And apparently, depending on the wattage, the type of light, if you have LED, if you have all these stuff, it produces different brightness, right? So we're talking about brightness here. And ultimately, the person designing that light bulb has to know how the amplitude of the light relates to the brightness of the light. So different bulbs have different types of lights, which influences the brightness of the light. Of course, you have a lot more going on. You have the wattage and stuff like that, but it does get very interesting when you're actually applying this to everyday life. But yeah, then at some point we bought a bulb we didn't like. It wasn't very bright. Then we're able to switch it out for a different one. So I was thinking at that point, man, amplitude matters, right? Because the amplitude of the light corresponds to the brightness of the light ultimately. Okay. Then you have the wavelength of the light. Different waves are actually characterized by the wavelengths. What is a wavelength? Like it suggests right here, I used to try to break up words just to kind of remember things. It's the length of the wave. or how mellow or how intense is that wave? Well, to measure the wavelength, you can pick 2 points. Either pick 2 consecutive crests or pick 2 consecutive troughs. So in this case here, they pick 2 consecutive crests, 2 highest peaks, or you can pick 2 of the lowest peaks and then measure the distance between them, and that will be your wavelength. The wavelength has a symbol, and this symbol here is called lambda, like a lamb and then da, da, lambda. Okay. So wavelength, once again, is the distance between 2 of the highest peaks of your waves or 2 of the lowest peaks of your waves, called the trough's lowest point, the crest, the highest point. What the wavelength communicates to us is how mellow or how intense the wavelength is, or the wave itself is. Okay, so to illustrate that here, to illustrate the difference, we're going to be looking at this right here. The wavelength later on corresponds to the energy of the wave. It also corresponds to the color. Okay. So I like to joke around. I like to actually use what I'm teaching in class outside of the context of class, because I feel like I'm trying to get some return on investment besides a paycheck, you know. And so when I'm out there, I'm like, oh, I'm really liking those wavelengths, referring to a color or music, right? I like to use wavelength to refer to music because there is a wavelength for sound, there is a wavelength for color. So sometimes I say things like that. People around me are like, huh? I'm like, don't worry about it. It just makes me feel better because I feel like I'm actually using this terminology for something in a regular conversation. Anyways, yeah, specific color has different wavelengths. And in biology class, you talk about that more, dealing with the color of chlorophyll, the leaf, and all the different dyes available in the color, in the pigment of the leaf, right? So remember, colors have specific wavelengths. Okay, even though we don't get into all of that in chemistry, not in detail, we'll talk about it briefly in context with the atomic model. So here we're examining different wavelengths, and in a way, we're looking at different colors too. The context here is not in clothes or in pigments of color, but in the atomic model. So from here, we're seeing that you have this wave A, wave B, wave C. Now, this first color to me, from my end, looks red. The second one looks yellow. The third one looks bluish. You can say purplish, or violet. I'll just say blue. Okay, so there's a correspondence between the wavelength and the color. I'm going to use the highest points here. You can see the wavelength for the red color is really large, right? So you can say this is a large wavelength. I'll compare it with the other extreme end. The other extreme end is the wavelength for the blue. This is a very small wavelength. Okay. So we'll talk about Roy G. Biv, but while we're here, Roy G. Biv is the order of the colors in the electromagnetic spectrum based on decreasing wavelengths. So red, which goes with Roy, the R part, this is red. This has of the colors, this has the largest wavelength. And then V, which goes with violet, if I can spell that correctly, this has the smallest wavelength. Okay, so how do we make these waves relatable besides the colors? This has to do with intensity of the wave and the energy at some point. So what I like to do when I was learning this in school, I was like, oh, I'm not very good at recalling. How am I going to remember this when I leave here? I know I have to know this for the exam. What do I do? What do I do? So I relate more to people, right? The colors thing, yeah, but the people thing is better for me. So what I did was I noticed the wavelength that was larger corresponded to a lower energy. And so I attributed the wavelength with people. So if you had a person that was chill, laid back, mellow, everything is cool with them, then they were people who were of larger wavelengths, low energy, chill, laid back. And then if you had more exciting people, the ones who just make everything so excited, as soon as they show up, the party starts. I want to say me, but me when I was younger, right? They invited me just to start the party. I'm like, yeah. When I show up, I'm like, where's the party? Yeah, very high energy, always talking all the time. They're the ones who have a smaller wavelength. They have a higher energy, and their wave is more intense, right? So of course, when I met my husband, I was like, yeah, we definitely are opposite. This would be me right here, intense wave, always up in something, doing something, trying to get something done. And he's always like, can we just relax, just chill, lay back, life is all cool. I'm like, no, we're missing out on everything. Everything is major FOMO, right? Yeah, so it's kind of like that. So I relate the waves to people, and that helps me remember that the more mellow looking the wave is more stretched out, it's more relaxed looking. The one with the larger wavelength is the one that has a lower energy. The one that looks more intense, more squished in space. You have many waves per small space. That's the one that has a higher energy, and that's the one that goes to blue. Guess what my favorite color is? Blue. That is just a coincidence. It has nothing to do with the wave. Anyway, you have bright light here, higher amplitude, and then dim light, lower amplitude. So then we have colors, right? Like we mentioned colors. And I mentioned Roy G. Biv, which we see right here, the order of the light according to energy. Violet will have the highest energy, and therefore it will be the hottest and also the hottest. Then red will be the lowest energy, and relatively the coldest. Trust me, if you get burned by a red flame, you will still burn. But if you get burned by a violet flame, you get very, very burned. Remember when they're using when men out there, I shouldn't say men, but when people out there are welding, they tend to use a flame that is a lot closer to the color violet because they're trying to melt through metal. They need a higher energy flame. So they don't use red or orange. When we're cooking, we're trying to cook our food not to just annihilate the food completely. So we slowly cook with most likely red, orange-ish, yellow region of the flames, right? So it's hot enough to cook slowly, but not too hot. You don't want to cook your food at this flame color because they'll just burn everything, right? Okay. I mentioned before, color of light is determined by its wavelength or frequency. And so we'll talk about frequency too in a moment. White light, as we know it, is a mixture of all the colors of visible light. So the colors that we see of visible light, Roy G. Biv, when you mix them all together, produce white light. They show that to you here. I remember when I was in school, somebody brought a prism to school in elementary school. For the first time I saw this, and I was like, whoa, this is so cool. They had a prism. They showed white light through it, and you could see the white lights separate, sort out into the different colors. Roy G. Biv, and you can see the G right there, right? Roy G. Biv. And I was like, whoa, that's so cool. It's like, yeah, the white light is made up of these lights right here. So you can do the reverse. Combine all of these to give white light, or the white light can pretty much spread out to give those. I had a meeting one time with people in art, and you'd be surprised, right? Artists do a lot of chemistry too, not too much, but enough because they deal with colors. And so somebody was saying, oh, my boss, the dean, was saying, what's your favorite color? Somebody walked in there and said black. And the artist said, technically, black is not a color. It's actually the absence of color. And I'm like, I'm not even going to walk into that. I'm just going to sit here and keep my mouth shut. But it was just very interesting how, they're talking about the white color being a mixture of all of these colors, but in their world, the black color is the absence of all of these colors. Therefore, it's just the absence of light, period. We don't go that deep in chemistry. We just define the colors that we see. End of story. We're told here when an object absorbs some of the wavelengths of white light and reflects others, the color that we see is the color that's reflecting. Okay, so it appears colored. the observed color is predominantly the colors is reflecting. So if you have a favorite shirt that has a is reflecting red color, but absorbing other colors. So the people who designed the color, the pigments that made that shirt, have to design the pigment using a chemical that has the reflecting and the absorbing ability. Okay. So we're now moving on and talking about different characteristics of the waves. Now we're looking at frequency. Okay, what is frequency? When you say, well, something happened frequently, the car passed through this area frequently. They went around, came back, and it was frequent over and over and over again. All you're talking about is a number of events happening over and over again, right? The context here back to waves is when you see a complete wave, how many complete waves? The number of waves that pass through a point at a given period of time. If you can capture that, if you can count the number of waves, then the more waves you have, the more frequent your waves are, or the higher frequency your waves have or possess. Okay? The number of waves equals the number of cycles. So frequency is essentially number of waves per second. So we want it passing through a particular point in a given period of time. So for us, that time will be per second. Do you have a whole wave pass through that point you're observing per second? Do you have 100 waves? Do you have 5 waves? Okay. How is frequency recorded? Since frequency doesn't really care about what the events are or what the cycles are or what your tracking is, the unit is just 1 over second or per second to give us freedom to observe different things. Okay. I remember when I was a kid, we used to play skipping rope, so you had to be very good at skipping. And so you could just count how many times the person is skipping per second. And that could be your event or your cycle, whatever it is that you're studying, right? How many times does a person skip per second? So once again, the event that you're measuring is undefined. So all we're tracking here is the number of events per second, written this or this way. The other way to write frequency is hertz. Now, in this generation, it may be harder to relate to hertz because we don't tune our radio, right? Back in the days of my youth, oh my goodness, you sat in the car, and when you got in the car, one of the most exciting things you got to do was tune the radio to get to your station. I mean, forget looking at the mirrors to make sure everything is okay, seatbelt. No, the first thing you do, turn on the car. Well, I couldn't drive, so it was like my dad's car. And then he turns the car on, and the first thing I do is sit in the seat and then reach out and then tune the radio. And I'm like, yeah, that's my jam right there. So you got your favorite frequency. Now people don't really have a frequency. I guess they have a channel. Same thing, I guess. It's not really the same. Then you have the energy of the wave. You can see this chapter excites me, right? It takes me back. You have the energy of the wave, and the energy of the wave and the frequency is somewhat related. Okay? Remember what we talked about back here. If there are many frequencies passing through an area, then essentially you have, so I'm going to relate the frequency, the energy, and the wavelengths to these pictures right here. Once again, top one here has lower wavelengths. It has higher energy, and it also has higher frequency. So the frequency will be written in a symbol that looks like a V that's slanted backwards. So I'll just say frequency for right now because we're still learning that. Okay, the other extreme here we have larger. Oh, I did the opposite. Oh, I did the opposite. Sorry. Here, this is the larger wavelengths, right? Larger wavelengths, lower energy, lower frequency. Because if you look at the number of waves here, it looks like we have 2 complete waves in that section that's sectioned out. Over here, we have a smaller wavelength, larger energy because you have many waves per section, And then you have larger frequency because the waves are passing through this area frequently. Here it looks like we have 2 complete waves. Here it looks like we have, let's see, 1, 2, 3, 4. It looks like we almost have 5 complete waves here. So you have 5 versus 2, right? So let's go with that. Larger wavelengths, smaller wavelengths. Notice that the energy and the frequency kind of increase in the same direction. And so that works that way. Okay, so back to where we were before I got distracted right here. The energy is proportional to the amplitude of the waves and their frequency. So the higher the energy, the higher the frequency. The lower the energy, the longer the wavelength. Frequency is proportional to energy. So when the frequency is high, so is the energy. When the energy is low, so I'll say here, lower energy goes with, that means inversely proportional, right? Goes with a longer wavelength. So I'm just going to go with, when you have a lower energy, I don't want to confuse this part, you have a higher wavelength. So hopefully that makes sense right here. Okay, so you want to know the relationship, you want to know the implications, you want to know how these go back and forth. Long wavelength, low frequency, short wavelength, high frequency. Okay, so from all of these relationships, we get this mathematical relationship right here. Remember, I told you guys the V doesn't stand for velocity here. This V here stands for frequency in context. Frequency has a unit per second. C is the speed of light. And then this is the wavelength. So what I'm going to do is I'm going to do some dimension analysis so you see how all of this works out together. Okay. With dimension analysis, remember with chemistry not being math, units really matter. We want to know what the units are because the units help to define the context of conversation. Yeah, we have a formula here. We have a mathematical relationship between these. Let me write this V differently because it is a different kind of V. Okay, with the frequency being 1/second, if this right here is 1/second, then the units have to map out. The speed of light, 3.00 times 10 power 8 meters over second. So I'm going to show you how the units map out. The seconds on the bottom here maps out to the second down here. And then after that, we have the wavelength. The wavelength will be some number in the question. The wavelength will have to be in meters, okay? So that these can map out. So in order to use this equation, I'll say correctly, if I can spell correctly, the frequency has to be in per second and wavelength has to be in meters. Okay? So hopefully you write this down because this is important. In chemistry formulas, just because you're given a formula doesn't mean you have what you need. You have to know the correct units. So in other words, in order for this equation to work out for you to get the answers correctly, the speed of light is the constant, so you tend to be given this in the correct unit. So that's why I didn't write that in the question. But over here, wavelength, because the wave is so tiny, it tends to normally be collected in nanometers. So you will need to convert to, right here, convert to meters from nanometers. Because remember, it is so tiny we cannot see with the naked eye. So if we wrote it in meters, it would be a very, very tiny number, and the chances of us making mistakes are very high. Okay, so it's converted to nanometers, so you're only writing about 3 numbers or 4 numbers versus 7, 8, 9, 10 numbers, where the chances of having error is high because it usually happens with humans transcribing a lot of numbers. Okay, but when it comes to the equation works when you have these units right here that I've highlighted, this unit and that unit. Okay, problem here. Wavelength and frequency. Calculate the wavelengths in nanometers. They want us to get the wavelengths, and we have to figure this out in nanometers. So let me actually write it down here. Wavelengths, which is wanted, in nanometers, of a red light emitted by a barcode scanner that has a frequency. This red light has a frequency of 4.62 times 10 power 14 per second. Okay, that's the frequency. Okay, so having this frequency, we're asked what's the wavelength. They didn't give us the speed of light, but we know the speed of light is 3.00 times 10 power 8 meters per second. Okay, I mentioned earlier from this equation, whatever lambda we get will actually be in meters, right? So my default will be in meters. This is meters per second. And of course, this is 1/second, right? So once I get my answer in meters after solving for this, I will then have to convert this to nanometers to get my desired answer. So remember, 1 nanometer equal 1 times 10 power negative 9 meters. Okay, now with this part here, I don't remember if I went over this with you guys, if I went over metric conversion with you guys. So what I'm going to do is I'm going to do a quick metric conversion thing, exercise with you guys. Okay, I'm going to pick a few metric prefixes, and I'll show you how you go from the metric prefix into an equality. Okay, so this is a quick detour that I'll come back to this because it's important for you guys to know this metric conversion. So for our metric conversions, some of these you do have in your conversion sheet, some of them you don't have. Let me pick let's see, kilo. I know kilo is in your conversion sheet. I'll start with a simple one. Kilo, I'll pick hold on. You know, I think you guys know centi. So I'll pick deci. Kilo stands for 1,000, right? And then it can be 1,000 whatever the base unit is. This is a prefix. Deci. Deci stands for, it's 0.1. So I actually want to show you guys how it works out with the conversion chart. So let me go ahead and detour for just a second here. Metric conversions. I'll combine what I'm doing with what they have right here, because I want you guys to get the hang of doing this, not always in an equality form. Oops, where's the one I wanted? That one here. They don't give it to you in an equality form. So let me see if I can use this. Oh, there, I can do that. Deci is 0.1, whatever the prefix is. Micro, of course, we have nano, which we're going to be using. Nano is 1 times 10 power negative 9. I'll do micro. This is a popular one because somebody was asking me, what do I need to remember? Micro is a popular one. That's 1 times 10 power negative 6. That is what these prefixes stand for. So these are the prefixes. I'm trying to think. They have new ones that I'm not even very familiar with. I'll also bring in G here for giga. Giga is times 10 power 9. Mega times 10 power 6. 1 times 10 power 9. Okay, so these are the prefixes. And from here, I'm going to make conversions. Okay. To make a conversion from a prefix, if you have a prefix right here, because you need a conversion to do a conversion factor, write 1. Okay. Oh yeah, for the conversion, let me pick a bunch of different base units. So for the base, I'll have grams. These are my base. I'll have grams for weight. I'll have liters for volume. What do I want to do next? And I guess I'll have meters for length. Okay. I'm it's Monday morning. I understand. I'm like, oh, where? I know the information is back there somewhere. Come back, information. Okay, so you can also use time. Like for time, the most popular one is seconds. So I'll pick from these four. Okay, grams, liters, meters, seconds. These are my base units. So remember, the metric prefixes tend to be paired with the base units. So my first conversion, I'll start with this one here. So write the number, usually 1. All of these tend to start with 1, 1, 1, 1. Okay. So 1, and then pick the prefix. Okay. And then the base unit. So I'm going to go with grams. So 1 kilogram equal. Okay. And then on the right, only write the unit that's the base unit, not the prefix. And in the place of the prefix, the 1 and the prefix, you can write what the prefix stands for. So here, since it's just 1K, K stands for 1,000, you can write 1,000 grams, like that. Okay? And then 1D, 1N, 1 mu, 1G, like that. So I'm going to pick different bases. For this one, why not L? So I'm going to have L on the right, and D, deci, stands for 0.1 or 8/10. So for this one here, since it's just 1 deci, each deci stands for 0.1. You can write it like that. If you don't want it that way, you can write it scientifically. Okay, that works too. 1 nano. Each nano stands for 1 times 10 power negative 9. Oh, I forgot to define the base. I'll make this m, 1 nanometers. So that'll be 1 times 10 power negative 9 meters, right? You see, from the metric prefixes, I'm getting conversion factors. Okay, 1 mu. What is mu? Let's do seconds. 1 microsecond. So 1 mu stands for 1 times 10 power negative 6, and then leave the second as is. You're only replacing the one letter, the one prefix, with the value of the prefix, because you're only dealing with one, right? That's why I say it's so much easier to put the number 1. If you put 2, you have to double it. That makes it complicated. 1 giga here. Let's see, giga. Ooh, let me use computer stuff here, right? At my base measurements. Bytes. Yeah. I don't know why I'm excited. I just am. Okay, 1 gigabyte. Should be 1 gigabyte. Here I'm going to have bytes. And then giga stands for 1 times 10 power 9. I was trying to mix it up, make it interesting. 1 gigabyte stands for 1 times 10 power 9 bytes. Okay, so hopefully you can see how these metric conversions convert into, metric prefixes become conversions. So we got this. Now back to what I was working on before I got distracted with this, but you guys need to know this. I need this conversion here. And that conversion is not given to me. So they're assuming I know it. That's why I gave you guys a little exercise. So remember, everything on the right here can be converted into this conversion based using the base unit they give you and the context of conversation, right? So back to this. Now I'm seeing I should have, let me copy this to the bottom. Come on, here. Copy. Okay, I need this down here. So from here, I have negative 9 meters, right? I'll add a page. I wrote too much, now I'm writing on a space right there. So hopefully you see how to get the conversions. So let's do our work. We're trying to find, I don't have the number they gave me. I need the actual number they gave me. Oh, the frequency. I need this number right here. 4.62 times 10 power 14. Okay. So 4.62 times 10 power 14 per second. I think that's what I got from here, right? Yeah. Okay. So for V equals C over, this is the frequency, lambda. I have this number. I have this number. I can get that number. So 4.62 times 10 power 14 per second equal, this is 14, 3.00 times 10 power 8 meters per second over lambda. Now to solve for this, since this is in the numerator position, I can actually just switch these out, okay? So lambda equals 3.00 times 10 power 8 meters per second over 4.62 times 10 power 14 per second. Oh, why do I keep leaving it out? I say 14 and I write 4. Anyway, there it is, right? So the second and second cancel out, and my answer is going to be in meters, so it's now worth doing my math. Don't forget these numbers are scientific notation. Put them in parentheses and it should work out. 3 exponent 8 to the right divided by open 4.62 exponent 8t to the right. This is 14. Ah, my handwriting. Now I can't even see it myself. Hold on. 3 exponent 8 to the right divided by open 4.62 exponent 14. Okay, so I got 6.49. My number is not in scientific notation. I have to count the zeros. 1, 2, 3, 4, 5, 6, 7. Okay, this is what I get from my wavelengths. Now they said they wanted in nanometers, right? So I need to do my conversion right here. 1 nanometer is 1 times 10 power negative 9 meters, correct? So I take the number I have right now, my calculator, divided by 1 exponent negative 9, which is what nano stands for, to the right, close parentheses, and I get wavelengths equals 649 nanometers. Okay? So you see how this is a much better number to write versus writing a number that has 1, 2, 3, 4, 5, 6 zeros. If you include the zero, the first zero before the decimal, 7 zeros. That one has a lot of error. This is a lot better. So when I do my math, that's the number I get. Let me see what they got. Oh, they gave you the conversion down here. Anyway, they won't always give it to you. Trust me, they won't. So you want to know how to work this out, and you want to know the conversion. Yeah, I got what they got. Okay. You want to know metric conversions, period. So I've been referring to this picture a lot. Please notice the way the electromagnetic spectrum is drawn right here. We have the low energy on the left. You have the high energy on the right. Low energy goes with low frequency and it goes with long wavelengths. So as far as I would say fear and emotions are concerned, the waves on the left are a lot safer. So I don't need this conversion. Um, these low energy waves are what I call, especially the radio waves, I call these the fun waves, okay? Here we have AM, talking about the radio. FM tends to be the higher quality radio. Back in my days, if you liked the FM station, you were more cool because it was a higher frequency station. It was a higher energy. It tended to be more clear, more crisp. You have the TV. What we see on TV, how TV waves are transmitted is through that wavelength. You have cell phone right here. So I tend to call these the fun waves because the things that we use for entertainment tend to be in that region right there. Lower energy, longer wavelengths, right? Longer wavelengths. So they're relatively safe. So years ago in my country, we weren't allowed to have a microwave because the government believed that it was bad for us as citizens, right? Because it is compared to radio waves in the higher energy level. As we go further right, we're getting towards a higher energy, right? And so we're told that you cannot own a microwave. So I remember coming to America and seeing a microwave, and my friend said, "Go ahead, put your food in there and warm it." I said, "No, thank you. I'll just eat my cold food." And then I didn't want to use the microwave. She's like, "Well, how are you gonna survive in America?" I was like, "I'll be fine." I know. I use the microwave now. I use it. I stand by the microwave. I'm like, "Hurry up!" I've become Americanized. Yeah. We do use microwaves now, but it was a time where we weren't really it wasn't, you couldn't even get it into the country because it's like, no, you can't have a microwave, right? Because it's bad for you. It's going to ionize your cells. So as we start moving right in this chart here, in the spectrum, you see the energy of the waves become higher, or they begin to increase. Now, while we couldn't use the microwave, we were constantly being bombarded by the ultraviolet rays from the sun. Now that way we could be all around. We could be in the sun, and the sun was really shining brightly all the time. You have infrared, you have visible light. So here's the thing, right? Notice that of all this wave, this is a very small part that we can actually see with our eye. This is our eye. It's hard to see that very well. Okay, it's our eye. So we can see this part here. See. So right to the left, remember this, the order here is Roy, G, Biv. So to the left of Roy, of red color, that's when you have your infrared. We can't see infrared, but this infrared radiation is to the left of Roy. And then to the right of violet is ultraviolet. So that's how I remember this when I was in school. Was to the left of red was infrared. We can't see that. So you have infrared, IR, then you have visible light, and then you have UV, ultraviolet, the one from the sun. Okay. And of course, you have microwave, which is a lot safer. And then the safest is your radio waves. I'm going over this because guess what? You have to remember this. Then you have X-rays. X-rays is the one, they use to find broken bones, to study your teeth right before they do a cleaning, or they do whatever it is they're going to be doing, drilling, whatever, to make sure the work was done well. So whenever I go to my dentist and they're like, "Oh, it's that time again for your X-ray," I'm like, "Yay!" Like, I'm not excited at all. And then I hate it when the the assistant is not getting the X-ray right. "I gotta do it one more time." I'm like, "Sis, really? This radiation, this is what's going through my mind, is right next to the gamma. If my government didn't allow me to be around the microwave, how many X-rays do you really need? I think the first one is just fine." Then it's like, "No, take one again." I'm like, get it right." So I'm happier when we're done with the X-ray, because in my head I'm thinking the X-ray radiation is very high. Think about the efforts we make, when I say we, to protect our skin from the sun because of the radiations and the ionizing properties of these waves. So imagine, right? I know they give you that lead vest. It's a tiny lead vest. They gave me a bigger one, and I was like, "Do you have an even bigger one?" And they looked at me like, "Wow, who is this person?" And I said to her, "A person that teaches chemistry." Anyway, X-rays is right here, right next to gamma rays. No, sadly, gamma rays does not cause us to turn like into Hulk and really strong and bulky, right, and buff. Sadly, overexposure to X-ray and gamma rays, even ultraviolet rays, can cause cancer, right? It does ionize your cell. It ionizes human tissue, live tissue, and that can increase aging, um, cause the formation of free radicals, and eventually cause things like cancer and stuff like that. So you have high energy waves, you have short wavelength, and you have high frequency. When people work in a job environment that has a lot of radiation, they usually have next to their badges a film, and the film keeps track of how often they have been exposed to the radiation. At some point, if it's too high, they're told, take a couple of days of vacation. It's kind of a reward, but it's also to kind of save them from overexposure. The light that we see is called visible light. It lies within the 400 and 700 nanometer region. And it's a very, very, very small part of the electromagnetic spectrum. So it is believed that cats can see a bigger range than what we can. I haven't actually seen a research paper that shows that. So it's not like I've gone out there to look for it, right? But I have heard. Remember, the shorter the wavelength, the higher the frequency, the higher the energy. Okay, so radio waves has the lowest energy, it has the longest wavelength. So my friend and I, who are such nerds, well, ish, we're trying to decide which phone carrier has the better waves, right? Because you have the different carriers having the different waves. We have AT&T versus T-Mobile. You have different price. I'm not gonna say who is who, but if you know it, if you have the carrier, you know it. One of the carriers, the phone calls tend to drop a lot. Okay, you're in the hello, beep beep beep. Seriously, again, I won't say who is who, but we're trying to match the unreliability of the carrier with the type of wave, and it's very interesting. It's very interesting. I'll just leave it as that. I don't want to influence you guys as one way or another. I'm not getting royalties for that, anyways. Gamma rays tend to have the highest energy. You have higher energy electromagnetic radiation, such as ultraviolet X rays and gamma rays. These can potentially damage biological cells. They tend to be ionizing. We'll learn later on what ionizing is, but yeah. Like I mentioned, you have to remember the order. Okay? So we're asked here, arrange the following types of electromagnetic radiation in order of increasing frequency, increasing wavelengths. And so let's go with increasing frequency. With frequency, we're going to have low frequency on the left, high frequency, because it said increasing, right? On the right. I tend to like to relate this to energy. So high frequency goes with high energy. That's when we have the more intense, right? Low frequency goes with low energy. Okay, remember how I told you guys, right? Visible light is essentially Roy G Biv, and then that's visible. I told you guys a lot about X-rays and how it concerns me, so you know that's really high energy. So X-rays somewhere here on the right. And then of course infrared, the one that has the word red, is right before the word red or the color red. So this would be IR, infrared. Okay, so as far as energy is concerned, we have infrared, we have visible, and then we have X-ray, the one that they take too much of, just next to the gamma rays, right? And this is increasing frequency. Done. Now, when they say increasing wavelength, the wavelength and the frequency are inversely proportional, so just reverse it. So you have low wavelength, high wavelength, if I can spell that correctly. This would be X-ray, visible, infrared. Okay, so it's a reverse of what we've been saying so far. Okay, after we have seen the wave-like properties of atoms, and we've seen how atoms can behave like waves, we'll see later on that atoms are releasing light. And the light they release, we call it just light, they're releasing energy. The energy they release can correspond to light, the visible light that we see, or it can be ultraviolet. It can be so many different radiations, okay? So after seeing all of this, what's the takeaway? The takeaway is atoms but release energy that corresponds to light, okay? With the energy released by the atoms, you have to match it to the pre-existing energy we have in the electromagnetic spectrum, okay? Either match the energy or the frequency or the wavelengths. So we'll work out problems where we're matching the wavelengths with the light release, okay? Let me go over here. So I want to talk about the photoelectric effect. This is Einstein's contribution ultimately towards the quantum mechanical model. His contribution is the photoelectric effect. Einstein observed during his experiment that when light is shined on a metal surface, electrons are produced from the surface. Now, the way the electrons were produced here, they were produced like particles. they kind of popped out of the surface. The electrons emitted from the metal surface are called photoelectrons because of how they are released. Because they are released by light. Okay? So to kind of go inside the atom, remember you have the atom, you have the nucleus, nu right here. Then you have the electron. We haven't learned much about the electron and its energy levels and stuff and how it can leave, but electrons can only leave the atom after absorbing a lot of light, high energy light. So yes, they can leave the atom, but they have to absorb enough energy. So if they absorb high energy light, they can leave. So these electrons weren't just leaving because they wanted to leave. They absorbed high energy light, and the source of this light was, the source of this energy was light. Okay, so it's really the energy they're getting here, which is from the light. So that's what they're called photoelectrons. This phenomenon is called photoelectric effect. So it's showing you what's happening here. Light comes from an outside source, goes inside the atom. The electrons are the ones that respond. They absorb the energy, and then some of them absorb enough energy to leave, to escape, and they emit it. Okay. So the photoelectric effect is the effect of the light on the electrons that allows them to be released. Now, a lot of light is being passed onto the metal surface where the atoms of the metal are. So please notice these are atoms of the metal. Okay? So the atoms of the metal are on the metal surface, kind of lined up together, not social distancing at all, packed together because this is a solid we're talking about. As the light is shown on the metal surface, the electrons inside the metal atoms are being released, not just one, but many. As long as you have light continually being shined on the metal surface, you have different electrons having the ability to absorb this light, and then they're leaving, right? They're escaping. As they're escaping the atoms, they are being drawn. So this is set up deliberately by the scientists to capture the escapee electrons. You see a lot of atoms here escaping and electrons escaping, kind of like they're being held against their will. That's not what's going on, but they escape. And the escaped electrons are captured by a positive terminal. Remember, electrons are negatively charged. The positive terminal is positive, so it's put there on purpose to draw, almost even assists the electrons to leave. They're drawn here and they travel through the metal that conducts them into the voltage source. The voltage source continues to maintain a positive charge on this metal even as electrons are coming through. So if this metal ceases to be positive, the electrons will not be drawn to it. So this voltage source maintains a positive charge on the electrode, or this pole right here. Electrons travel through here and they're registered on the meter, the current meter. Remember, current is electricity. So this meter is actually saying electricity is being generated. Well, how do we get electricity being generated? Electricity is essentially generated when you have moving electrons, because the moving electrons release an energy that's called electrical energy. So essentially, electricity is formed as the fast moving electrons continue to move through the conductors. Okay. And at some point, they get back here, they keep getting released. Okay. So here, current is being generated. So light, let's see, light causes electrons to be released, and then electrons eventually cause electricity to be formed. So where do we see the technology applied? anything solar. So when you have solar panels, solar this, solar that, solar is just a way of monetizing. And I'm using the term monetizing because that's a new word that I've been learning recently, right? When I talk about the financial world and stuff like that, anyway, is monetizing this knowledge. You're taking this knowledge and you're trying to think, what can I do? How can I develop a device? How can I design something that will actually create something useful that will eventually generate money, right? You generate electricity here and then eventually money. Okay. So we're told here Einstein proposed that light energy was delivered to the atoms in packets called photons or quanta. Oh, I'm right there, right? So the energy of the light ultimately influenced how many of these electrons were going to be released, the amount of energy that was being applied to the surface of the metal. So what I'm going to do here is I'm actually going to start talking about this right here when we meet on Wednesday. I don't want to go any longer than necessary. I'll just stop right here. When we meet on Wednesday, we'll go over this concept here, and then I'll write start here for Wednesday. And then we'll go into the photoelectric effects some more, work out these other problems. Let's see. I think I already worked this out, so I don't need to work that one out again. Yeah. We'll go into the rest of this chapter and talk about Bohr's model finally, start talking about the quantum mechanical model. Hopefully we start getting into that on Wednesday so that we can actually at least see the quantum mechanical model more than one time. Yeah. Okay, so I'll end here for today. We'll talk about the rest of the photoelectric effect on Wednesday and then go into the rest of the chapter. Okay. Do you have any questions? It is already 11 o'clock. I mean, it's 11:02. I didn't want to go any longer. Okay, you're welcome. I'll see you Wednesday.